Okay, so I will be doing Form 5 Chapter 4 because I skipped the lesson when my teacher was teaching, and I'm somewhat confused by this chapter, so hopefully as I progress in this series, I'll be able to understand. Now, mark the direction of current flow in copper rod when the switch is closed. Okay, so we have to know that current always travels from positive to negative. It always starts from positive to negative. And electron is like the opposite of current. So it will be from negative to positive. Okay. But we don't need to know about electron right now. We just need to know for current. And in chemistry, we learn that the long branch or the long strand is the anode, which for electrolysis is the positive terminal in this case. So this is the long branch, this is the positive terminal. It means that current travels here. Okay, so it should be like that. Next, in which direction will rod PQ move? So you can determine this by doing the Fleming's left hand rule. So your index finger, which represents the magnetic field, which is from north to south, should be pointed down. And then all that stuff is the current, which is from Q to P, so it should be in you. Okay, half of this is ChatGPT, okay? Because at first I thought it was going to go to the left, because like it's out of the current, and then somehow it convinced me that it was like it's supposed to point towards you. So this means that the force, that your thumb would be to the right. But the answer scheme says that it's rod PQ will move away from the magnet, which is kind of funny because we don't know where it will move away from. So for this question, I will be asking my teacher and I'll get back to you guys. Now name the rule that is used to determine the direction of movement of copper rod. It's very easy. Fleming's left hand rule. State one way of increasing the speed of the copper rod. So we can do this by increasing the strength of the magnet or by increasing the current. It's also in the textbook, if I'm not mistaken. So stronger magnetic field, larger force, larger current. Okay. So you can give either you increase the current or use a stronger magnet. Because remember, we are talking about like Fleming's left hand rule, and you know how this represents the force, this represents the magnetic field, and this represents the current. So what affects the force? Of course it's the magnetic field and the current. So when you want to increase the speed of the copper rod, because you want it to have a higher force so it can move whichever way it moves faster, then you have to increase these factors. Now this question, I was like, what? So diagram 4.1 shows a new diamagnetic ball released on a copper metal track. The neodymium magnetic ball moves down the track and stops at point X. Okay. State the physics law involved. Apparently, we only learned like 3 laws in this, so it's between like Faraday's law and Lenz's law. But Faraday's law is talking about the effects of like what will affect the induced EMF. Wait, no. Faraday's law states that the magnitude of induced EMF is directly proportional to the rate of cutting of magnetic flux. Okay. However, here there's like a phenomenon, and for Lenz's law it states that the induced current always flows in a direction that opposes the change of magnetic flux that causes it. So apparently the answer is Lenz's law. Okay, the reason why, I'm not sure myself, but I asked like ChatGPT, and it said that because there's like a opposite movement, because it opposes, there's an induced current, it forms an induced current, and it opposes the change of magnetic flux, so it like stops there. And that's about like what I've got from it. Now, by using electromagnetic induction concept, explain why the ball stops at point X. Okay, so the scheme says that the relative motion, okay, between the it's a magnetic ball. No wonder, bro. Okay, now I understand. So basically it created like a magnetic flux, and when you have a magnetic flux, it produces an induced current. So then the induced current, it always flows in a way it opposes the change of magnetic flux that causes it. So let's say there's a magnetic flux here, and then there's induced current here, and then like it stops, like because you're both opposing each other, and because this is a coupled metal track. Okay. So the relative motion between the neodymium magnetic ball and the copper metal track produces an induced current. I think the keyword here is relative motion. Okay. Next, the induced current forms an electromagnetic field that opposes the motion of